Hi, I'm Elaine. Welcome to my podcast channel.
We are going to start with some basic math questions. So first, I'm just going to ask you to self-introduce yourself. Like which branch of math do you specialize in? Which university and role are you in? And like describe your math field and your role and why are you interested in your branch of math?
Yeah. So my name is Matthias Doerrzapf. So I'm an applied mathematician. I'm at Cambridge University, and within Cambridge University, I'm in one particular college called St. John's College. My main interest, I would consider myself as a very broad mathematician. So I have a lot of interest in different areas of mathematics, but probably the main areas I should mention are algebra on the one hand side. I did a lot of work also in quantum field theory, so in theoretical physics, which here in Cambridge is very strong within mathematics. So these are mathematical structures within particle physics that we study. And a lot of the very famous quantum field theory and quantum mechanics even that was developed in the last 100 years, of course, came from Cambridge, came from the applied maths department here. I've also worked in financial mathematics and, worked in random walk models and, financial modeling. And that's, a really broad spectrum of mathematics. And I think, and perhaps later we can talk about this a bit more, but if as a mathematician you have a very solid foundation in what I consider as the two big pillars of mathematics, that's sort of linear algebra on the one hand side and analysis on the other hand. If you have a very solid foundation of those two fields, you can, work in almost any area in mathematics, and you will, almost any area of mathematics will be accessible to you.
Right, totally. I totally agree. Like mathematical ideas, they're really interconnected. And if you have very strong basics, especially, you will like develop, especially as a foundation that you build up throughout time. And I'm thinking that undergraduate studies such as real analysis and linear algebra, I've heard it's really important to master.
Yeah. Now, you also asked about my roles within the university. So obviously, I'm a mathematician. I teach mathematics. I examine mathematics. I, create mathematics and research. But I'm also very heavily involved in student support. So for the college, I teach students individually. Even that's what we do in Cambridge, and we teach in very small groups. We meet our students. I, direct their studies. So I'm very heavily involved in really meeting students individually and running also a number of scholarship programs and exchange programs and so on. Some of these are research exchange programs, where some of my students go overseas, for example, to Caltech and National University in Singapore and so on, and do research projects there. And I'm also responsible to run, these sorts of programs.
Oh, wow. That is really, really impressive. I'm also really curious, like, what is your typical day as a professor like?
Oh, is there anything like a typical day? There, I've, as I said, I have various sort of roles, and these roles, they come and go at various stages in the year and different days. So there isn't. So the typical day depends, of course, where you are in the academic cycle. And today is a Saturday, and I was in the college actually teaching quite a few of my students. I had one online lecture earlier in the day, and then later on I taught 3 groups of my students in my own room in college.
Oh, wow. Wow, that's really interesting for sure. So let's move on to our next question. So what are some examples of various sublevels, like studies, as in, like, because we have so many math subjects, how would you subdivide all our, like, the holistic mathematical field, like, so big?
Yeah. So, obviously, the 2 most important sub-levels I have already mentioned. And as I said, I'm a strong believer, linear algebra, the study of vector spaces, linear maps, linear systems. And those are, of course, everywhere, and they're naturally everywhere. A lot of things are linear, but even if we have models that are not linear, nonlinear models are sometimes very difficult to solve, and you see them obviously in the sciences and in lots of applications all the time. But what if we can't solve the nonlinear problem? We of course linearize it. We look at sort of the tangent space, the linear space, and I remember when I was a student, I didn't like this at all. I thought, but this is not real. That makes, it's wrong to do that. But actually, really thinking about working with this concept, it's actually a very good thing to do, because that locally, almost every space will look linear, and you can treat it like a linear space, a linear problem. You don't always know what local means. I mean, sometimes local could be far. Quite far, but sometimes it means very tiny environment only. So, of course, you need to know what local means. But locally, almost anything looks linear. So that's why, of course, linear algebra is such an important, sub-level. The other one, of course, analysis, study of limits, and it's, very different concepts, of course. And, that's why, of course, some mathematicians, they love algebra more. Others love perhaps analysis more, just because.
I was wondering why you even chose, applied mathematics is astoundingly excellent and really hard, I guess. Why did you choose, there's pure mathematics and applied mathematics. Why did you choose applied over pure or others?
So the borderline between applied and pure is anyway quite artificial. And an applied mathematician also has a very strong understanding of algebra and analysis and, the core subjects. Perhaps what differs between applied and pure mathematicians is more the approach. When, as an applied mathematician, very often I want to get so familiar with the problem. I would perhaps run computer simulations to sort of understand the problem. Ultimately, I also want to prove it, just like a pure mathematician, and using a rigorous proof. So, and I think here we are the same, applied and pure mathematicians. My publications would also use, rigorous, proving techniques to prove your result. But perhaps the approach to get close to the result is different. Obviously, I'm interested in using sort of my mathematics in problems that are probably derived out of either physics or the sciences or economics. And that's where I take my problems from. And that probably makes it an applied mathematics area. Whilst perhaps a pure mathematician takes his or her problems, intrinsically somehow out of, the pure mathematics context. So again, the approach is perhaps different, but I think the result, both sides are, very rigorous. So
for sure.
The mathematician is rigorous. So in this sense, I would really say that the borderline is not very, very clear. And I remember very well when I was at Harvard, I collaborated with people in pure mathematics at MIT, and they were very pure mathematicians in algebra. They were interested in the same problems, and me as an applied mathematician, we shared this interest in these problems, looking at these of these conformal field theories, wanted to understand them. So the interests are the same, and the methods are perhaps slightly different, but in the end, the theorems we work on are similar, probably the same theorems.
I'm really surprised because I thought they're so divided in a way, like how they're just enemies in a way, but they actually collaborate.
I have some pure mathematicians that are very good friends. We are not enemies. No, we do collaborate. But as I said, I think the methods are perhaps slightly different, and the problems are taken from, perhaps I take my problems more from the scientific side.
Yeah. So I've heard another someone say that mathematicians rarely argue because the reason and logic is really, really clear, as opposed to a lot of scientific fields, they argue a lot. Is that true?
Yes, I think I would agree with that. I mean, we have our, obviously, if we go through our sort of line of reasoning, there might be mistakes in there, so we might argue about whether there are any mistakes or not. But I mean, these are all very factual things. So it's not that we are arguing about a belief, it's, if we lead our sort of line of arguments, if we lead our proof, we can only discuss whether, certain implications are right or wrong, but it's not about, that, I believe that and you believe that, if that makes any sense.
Right, for sure. Like math is just right or wrong. It's really, really clear logic.
Yeah. Well, it's not always like that, but if we have, a well-defined axiom system and we base it on this axiom system, and then, we should be able to derive, in logical way, and a logically correct way, we should be able to derive our results. And there should be very little space for any arguments.
Yeah, which is really good. I mean, as opposed to the scientific fields, too many debates and arguments about things.
Yes, but that's I think that's really the strength of mathematics, to basically cut your axiom system down to the minimum that is really sort of required to make this work. And I think that's really the strength of mathematics, to really find out what are sort of the basic underlying rules or axioms that make it work. Whilst you don't have this in the sciences in the same way, just because very often you can't base it on axioms, and you base it on experiments, and experiments are very often, there's a lot of space for interpretation, so you don't have this clarity, because sometimes you can't even reproduce experiments, or you get different answers if you perform the same experiment, and you have these uncertainties which shouldn't happen in mathematics.
For sure, yeah. So I mean, connected to this question, looking further away from our near future or distant future for 50 years, what changes in the math field do you expect? Like any big changes or big discoveries? Are there any progress in your research fields?
So I think this is, of course, I mean, in applied mathematics, I would say these developments will, of course, be led by sort of the need where the problems arise. And for example, now, I mean, when students, or whenever I give sort of talks about mathematics at schools, I'm so very often being asked to predict where mathematics will be going. And 50 years is difficult, but let's just look at 10 years first. And I think what the pandemic has also shown is that biology, for example, needs a lot more mathematical skills, and all the modeling behind biology that we had to do during the pandemic. It's very heavy mathematics. Dynamical systems are very important there. But then, a lot of other areas, DNA research and so on in mathematics, really requires, in biology, requires a lot of mathematics. And I see a lot of my students going into biological research programs, doing PhD in biological areas. And that's already happening now. So I think this will be a trend that will be even a lot stronger in the next decade, say. 50 years from now, that's of course quite difficult to predict, because where will the needs of come up? Of course, what has changed, say, in the last 20 years is that we have a lot more computing power, and if you look at the computing power that is available. And I think a good example is if you look at artificial intelligence, which is of course everywhere at the moment. Everybody wants to go into AI. It's very trendy, and of course, a lot of work needs to be done. But if you look at the algorithm, so neural networks existed already 30 years ago, say, and at that time, they were not very successful. We knew the algorithms, but we could not use them very well. And that's because we didn't have the computing power at that time. They need a lot of data, they need a lot of computing power. And now 30 years later, we have it. And suddenly, these models can be used in various areas of, almost everyday life, you would say. So, mathematics that perhaps already existed, at least partly or partially 30 years ago, is suddenly being rediscovered just because of having more computing power. And that's, of course, something I can clearly see, continuing over the next decades.
Which is really scary. So related to your our discussion about the computer programming and AI, artificial intelligence takeover. Do you think that mathematicians in the near 100 years or whatever in the near future will still be needed? Will we be replaced by robots?
No, we won't be replaced by robots. I mean, all what computers can do, all what these algorithms do, they can just follow the rules, but they cannot make the rules. And I'm a strong believer that if you look at the semantic behind something, the understanding, the computer can't do this. The computer can only do the episodic part of the memory. Computer can have big memory and can follow rules. The computer can't do the semantics. So if you think about language, you have those two parts of language, the semantic, the understanding, and of course, the episodic side where you just repeat things. And computers are very good at that. And they're probably better than we are in remembering things, and they can help us there. But of course, in order to that's what we said, earlier, also at the very beginning, mathematics is about understanding structures. It's really about the semantics and how these things fit together.
Because humans are more creative. Yeah,
computer algorithms don't do this at all, and I don't think they will be able to do that.
Yeah, it's kind of scary. I thought that maybe humans won't be even needed in the near future, but they're still really necessary, actually. And also another question. So related to what one general advice would you give to modern high school students in the UK or in Canada or in the US, like high school students in general studying mathematics and they just want to be a theoretical mathematician, or they want to go into a field that is related to the math branch?
So I think what is extremely important, trying to become a mathematician, what is probably one of the most important parts of this is to be able to discuss mathematics. And I think schools and other organizations, they try to train people to do mathematics, but for me, actually explaining mathematics, discussing mathematics with others is actually a lot more important. You learn most when you discuss your ideas, your understanding with other people. And I think that's very often lacking, in the preparation for, say, university degree. Because what we really want is, once you're at university, that, this independence. So, independently thinking about these mathematical structures, developing your own mathematical structure. And that's quite, the transition from sort of school mathematics to, this independence that you can say, rather than asking your teacher, well, teach me the answer, you should actually at some stage tell yourself, oh, I can crack this myself. These are the definitions I need. These are the structures I need, and I can, the teacher should give you the ability to crack this yourself. But in the end, it should be you who works it out, and that's very different. And I think a big part of this is being able to, present mathematics, discuss it with others. So as part of my teaching, I always get my group of mathematicians in the college really together in a workshop style thing already at the very beginning of their mathematics career, in the first year already, and give them sort of a forum where the 15 of them can really discuss mathematics and present their ideas and learn also from others. And even for me, even if I'm in a lecture theatre with 250 students, when you present it to others, that's when you really realize that when you logically lay out the arguments in front of others, that's when you realize whether you have really understood it. And sometimes you realize you haven't understood it, and then you do work on that.
Yes. Have you actually ever been talking about a mathematical concept upstage, and then you were like, oh no, I don't think I really understand actually. Can I?
That happens all the time. Even in lectures in front of a lot of people, that can happen, that suddenly you realize actually it's not quite right the way you think about it. But it's really that moment. I think if you just sit there and think it through in front of a piece of paper, that's a different process. If you are in front of other people and you communicate with them, that's actually a very different process if you lay out the arguments then. So I think this is one part that in preparation of a mathematics course is very often missing. And that's where, I would recommend that, people who are really students who are interested in studying mathematics at university, that they really do this and, discuss with others at school or in their social environment, people who have also these sorts of interests, and really discuss mathematics and discuss their thoughts.
Yeah, that's really important. Like, I think a lot of students are hiding away from expressing their ideas because they're really scared that they might get a number wrong. So, or maybe if you just say something wrong, you will probably feel stupid or whatever. So I think that it's really important for students to actually just blurt out their thoughts and then express their ideas as well.
Right.
And also in university, they have a specific academic paper writing style. Like, suppose that this, we have that. Like, there's like a format or structure or academically mathematical language. And then as opposed to high school, we just don't have that kind of stuff. We just have this is my calculation, and then nothing is there. But in university, it's really, really formatted.
Yeah, and that's part of the transition. Now, different mathematicians have probably different styles, and we don't all use the same style. I think some people are probably sort of more rigid in the way they express their mathematics than others. So sometimes it's okay to use English words, or just to use words in between as well.
Yeah.
But there are some mathematicians, they wouldn't want to do this at all. So there are different styles. But you're right. The logical arguments have to be correct, and there may be variations how you can express them, but the logical arguments have to be correct. Whilst of course in school mathematics, that's very often not the case, that the logical arguments are used sort of in the correct order. Whilst at university, that's definitely what we want to get right. So if you want to prove, a statement A is correct, then it's not enough to use your statement A imply something that is correct. That proves nothing about statement A. So you have to start the other way around, something that is correct, that leads to statement A you want to prove. And for, at university, we need to get these sorts of implications and equivalences right. I don't think at school level, the mathematics is so rigorous that there's put so much attention to these points.
For sure. Yeah, that's why, because a lot of students who actually excel in high school basic math, and then they just suffer in university math and they just give up. And I think that, yeah, I know a lot of mathematicians or like math students, and they just give up when they're in their masters. And I think it's really a pity. I think they should continue to persist. So I think persistence is so important. And like, why do you think some people even give up? Like, is it because of their limited time, like, or they just find it too hard?
Well, I'm not sure I would call it give up. I mean, what I see is, of course, university is also there to give you space for development. And obviously, you start your university course with sort of certain ideas what you want to do, but then university is there to offer lots of opportunities within your subject, but also, education opportunities outside your subject. And I think that's very, very important, that a university course allows you that space of development. So I would say among my students, probably maybe 30% of the students then develop in slightly different directions than what they had envisaged. And that I wouldn't say that this is led by dropping out or giving up. It's led by, having opportunities that develop their interests in a slightly different way.
Yeah.
And that's positive. So, I always see
for sure.
rather than so. Because school mathematics is actually so different from university mathematics, it's not quite clear what to expect in school mathematics, and obviously in university mathematics. And obviously school mathematics is some indication, but it's not 100% indication if you love school mathematics that you will like university mathematics. Given that there's so many opportunities for development at universities, so it can easily happen that people develop in other directions.
For sure, yeah. And also a question that there's this huge problem, PNP problem. Have you it's like a really debated big math problem, which is P equals to NP or PNP. Like, what are your thoughts on that problem?
So what is the problem?
PNP problem, or like it's like a really debated math idea in this math field.
Yeah, I'm not sure I know which problem you're talking about.
Oh, it's okay, but it's like I was wondering, yeah, like, do you have any what's your favorite math theorem though? Like the problem that you really are so interested in?
If you ask me for my favorite theorem, I would say that's probably Noether's theorem.
Mm-hmm.
And Noether's theorem, so Emmy Noether, she was a mathematician in the, I think, 1900s or 20s and 30s. And the reason why I like this theorem so much is because, the theorem says that whenever you have a conserved quantity, say in a field theory in physics, a conserved quantity like energy, like momentum and so on, and then there's an underlying symmetry, and symmetry is, of course, a group operation on your quantum field theory, and she could prove that. And of course, what I find so fascinating about it is that it really connects, experiments with something purely algebraic, and that's, I think, rare, where you have, very hard pure mathematics connected in this direct way, and it goes both ways. So she could prove that you have conserved quantity and then you have a symmetry, but also the other way around, you have a symmetry, you have a conserved quantity. So if I go, say, to CERN and perform some experiments there, and I find, something is conserved, we don't quite know why, but it's conserved, then her theorem tells you that there will have to be a symmetry on the system. So there's a symmetry group that you apply to that quantum system that keeps it, so there's a group you apply to a system that keeps it invariant. And I find this, amazing that it connects, real world experiments so directly with a, very, very deep algebraic concept, like, out of group theory. It's a theory that doesn't get so much credit, and yet it's responsible for, a lot of our very fundamental things, like energy conservation, momentum conservation, angular momentum conservation.
Wow.
And a lot of, very deep concepts. Our understanding of a lot of things around us depend on, relies on exactly this theory.
That's amazing and wonderful. Who's your favorite mathematician? Is there, I know you're a really outstanding mathematician. Is there a person you very admire out there?
Favorite mathematicians? Well, there would be loads, but if I have to mention one person in my field, it would have to be Dirac. I would say Paul Dirac, who got obviously a Nobel Prize. And I mean, quantum mechanics wouldn't be what it is and how we would understand it without him. Obviously, there were others who were instrumental in developing quantum mechanics. But I think so the big achievement of Dirac is really to, show the algebraic side of quantum mechanics. So, obviously you can solve Schrödinger's equation, and if you solve Schrödinger's equation for the hydrogen atom, you get, all the atomic orbitals. You basically get the whole of chemistry out of one equation, if you like.
Wow.
But that's solving, a differential equation. And of course, Dirac showed that all this is equivalent to an algebraic problem, and combines, the differential equation approach of quantum mechanics to his algebraic approach. And I think that's a big achievement. Obviously, he has many other achievements as well, but I think this is a massive achievement. So yeah, I would vote for Dirac then.
For sure, yeah. Oh, I I'm pretty sure that you have a lot of students, like hundreds or thousands over your whole academic teaching industry, or um, is there a student that really who's like really talented that really captured your attention, and then or
Well,
postdoc?
I obviously had loads of students over the years, and Cambridge gets a lot of very talented students. It would be difficult to point out, just one
Yeah.
particular one. I mean, if I look at what my students do, quite a few of them really stay in research, and I think the numbers. So if you look at, say, undergraduates that come to Cambridge doing mathematics, I don't have the exact figures, but so by experience, I would say maybe about 20-25% of the students in the end really end up, doing research. Most of them at universities, others perhaps in industrial setup. And that's a very high number, say a quarter of our students. I'm sure this is higher than most of the other top universities. And there's a reason for that. Obviously, there's a lot of research happening here at other universities probably too. But here we know our students extremely well. I only take 15 students a year, so and I teach them really sort of individually. I know them very well, and having this exposure to your professors already at this very early stage, that you're known by name by your professors already in the first year, and you meet them individually, and I think this leads to the result that a lot of our students get interest in research already at a much earlier stage and are more passionate about research too. So a lot of our students stay in research, and if I look at my students, some of them are now professors at Stanford, others are professors here at Cambridge. So another one of my students is a professor at Caltech. So I had some of my students got into a very high level position at top universities. But even if you look at what my students otherwise do, they go into very interesting positions, say in innovation, entrepreneurship. Also here you find a lot of mathematicians who have some great idea and have the ability to sort of manage to realize these ideas as well. And but maybe having a great idea of a product they could produce, but really manage to lead this through. So I have a lot of students who actually go into innovation in particular. And yeah, I don't mean just working for sort of big companies. I don't want to mention any of them. Really setting up sort of their own sort of startups and taking ideas through. So obviously there are also a lot of mathematicians going to financial sectors, because of the financial sector or insurance sector, they need a lot of mathematicians because it's very mathematical, the modeling. So a lot of my students would also be successful in these routes.
Yeah, so I was wondering what commonalities or common qualities do you find in all of them? Like, do they highly concentrate? Are they super creative?
Creativity is clearly one of the sort of very basic skill, I think, of mathematical education. Something having this understanding combined with creativity is clearly something that's being very well developed if you study mathematics. Analytical skills, being able to visualize things, I think is very important. I think mathematicians, they can easily, solve problems in 4 or 5 dimensions without the, and they can visualize that. Even though, of course, it's, I think without sort of the mathematical skills, it's probably difficult for anyone to visualize anything that goes past 3 dimensions. But I think mathematicians have or develop the ability to sort of think in this abstract way and can sort of visualize this even in higher dimensions or visualize complex systems.
Yeah, do you think these like there's complex systems and higher dimensions, do you think they could draw these diagrams specifically on the blackboard? Is it presentable, or it's just really highly theoretical?
Well, it of course depends what you mean by visualizing it. I mean, if you put it, if you want it drawn on the blackboard, how do you can visualize cross sections, or if you use 3 axes, how do you visualize your 5-dimensional problem in 3 axes? That might not be possible.
Yeah.
But I think mathematicians, if I give you now, say, the problem to calculate the intersection volume of, say, a 4-dimensional cylinder cutting through a 4-dimensional sphere, and a mathematician will be able to calculate that.
Wow.
And in order to calculate this, the mathematician somehow has to visualize it, even though you can't draw it. But of course, you know immediately what I mean, right? You've got the 4-dimensional sphere, so you know what this sort of would look like, and you've got a cylinder going through that, and it gives you sort of an intersection volume, which is of course 4-dimensional volume. A mathematician will be able to visualize it somehow and work it out using the appropriate integrals to work out what that would be.
Yeah.
Even though, of course, you can't draw it. I mean, how would you draw it? You can't draw it. We just
yeah.
active, so
yeah. So were you really interested or mathematically passionate since you were a young child? Like, when did you start committing to, like, I want to be a applied mathematician?
It's an interesting question. I wanted to do loads of things as a child, and I wanted to be a pilot and a teacher and lots of things, I think. And I don't know when I really committed to mathematics. I think even at the start of my university career, I did lots of things. I did a lot of sciences as well, particularly physics. Hence, I have this, interest in the foundations of quantum field theory. I think it was only at a later stage when I really sort of committed to mathematics. A later stage, probably meaning once I entered probably a graduate degree, that I really knew, this is where I want to do a lot of my work. I think I benefited a lot from a very solid foundation, particularly in the topics I mentioned, like linear algebra and analysis. And I was lucky to do this because I don't think as a student I realized just how important a broad and solid foundation is. And I think I just had the right advice from the right people, the right professors giving me the right advice, and I was lucky. And got this very solid, broad foundation that sort of allows me now to work in various areas of mathematics, and that probably ultimately, determined that, I found my way sort of into mathematics and stayed there.
So obviously went to Harvard University. Do you think what good math programs do you think Harvard or Cambridge provides for students?
So of course these are very different universities, and I love both of them. I mean, both of them are in Cambridge, of course, different Cambridges, but but I mean they are different programs. I mean you're particularly talking about, say, the undergraduate programs. They're of course different programs. The Cambridge mathematical course, we call it mathematical tripos, is of course a world famous course and is a very deep introduction in mathematics. Whereas of course Harvard is still running, liberal arts education. You can mix and match things, and I think for different students, it's it depends on the student what you want to have. So the universities are structurally very different. Of course, in terms of research, there's top research happening at either of these institutions, and once you talk about graduate degrees, you can. You have wonderful mathematics being created at at Harvard, but at the same time at Cambridge too. And obviously research groups interact as well a lot. So obviously I know lots of people at Harvard now too. But I think if you look at the undergraduate program, there is a difference, and you really need to sort of make up your mind whether you prefer the liberal arts approach to our approach being, we give you a very broad mathematical education first, very deep, but it is limited to mathematical topics, and you would not have the possibility of mixing, matching this with a number of other things. Some students love this and they are ready for this. Others, they they want the flexibility of a liberal arts education first, and then go into mathematics deeper at a later stage. So I think it depends on your interests and whether you're ready for this or not.
Oh, okay. So basically, I've heard that Oxford and Cambridge, they both universities, they offer very good math programs. Do you think they're really similar as well, like Oxford and Cambridge? Do you think their programs are pretty similar?
So I'm probably biased here, but I think so Cambridge, I think the advantage of the Cambridge program is our 4th year. Our 4th year is an extremely famous course. We call it, so colloquially, we call it Part 3 mathematics, but it's actually an integrated master's program. And if you just go to the internet and look up Part 3 mathematics Cambridge, you will see that this is indeed a famous course. A lot of really big mathematicians worldwide, very famous mathematicians worldwide, would have taken this course. And it's a fantastic course that offers you access to perhaps 100 different very very deep graduate courses. And I don't think at any other university would you get a collection of such a breadth of mathematical areas at that level in a 1-year master's program. And that's the advantage of Cambridge. We have our Part 3. They also, of course, have an integrated master's program there, but it's not quite the same as our Part 3. So I think, if you want to get into mathematical research, then certainly our 4th year of the undergraduate program, this Part 3, is the ideal preparation for it. And for this 4th year, we of course have not only our own students doing this 4th year as part of their undergraduate degree. We have a lot of students coming to Cambridge from outside Cambridge, so from the big universities worldwide, and they join us. So we have actually more students joining us for Part 3 from outside Cambridge than our own students carrying on. So I think here we are indeed different with to Oxford, because we have this really stellar 4th year course. But if you just look at a course, just take an algebra course, say at Cambridge or at Harvard or any other university, beginner's course in algebra. Of course, the theorems, the proofs are all the same. I mean, they're hundreds of years old. So our theories we teach in the beginner's course in algebra are not different to the ones you would study at Harvard, say. But the approach is very different, what we do, because so the approach to teaching and learning is very different. So we teach, obviously we have the big lectures like at other universities too, but we teach in group size 2 then. So, if you're one of our students, then you and your supervision partner would meet the professor in probably the professor's room for a whole hour. And that's when we can really focus on your ideas and your understanding. And here, we are really different to other universities. And it's not just the small group size that is different. It's that these sessions, they're not assessments. So we don't have continuous assessment. So you can go into this session with your, supervision partner and your professor free from assessment pressure. You can really, basically freely sort of discuss your ideas without having the concern that if you say something wrong, you would not get the marks, because you're not being graded. There's no assessment, and it's really conversation between you and your professor. It's very small setup. So that's a big difference between So as I said, it's not necessarily the course content that differs. It's really the approach to teaching and learning that differs to other places.
So tons of discussions with professors, and it's I guess you have a lot of one-on-one personal discussions with your students, which is, I would say, the most fun part of math. I would say
that's right.
Yeah, for sure. Just another last question we have here. Do you think that high school students right now, because they have high school mathematics is like pretty basic, do you think they should go into mathematical research with professors at universities and do some research and do some work? Do you think they should do that at this stage, or they should do you think students should right now just accumulate their knowledge by reading a lot of math books?
Yeah, I think working on a research project really only makes sense when you're ready for it. So
Mhm.
sometimes I'm not sure. I mean, if people are ready for it. I mean,
Right.
research, of course, means that you're not just being given the answers. You put your own ideas into it and you try to work it out, and you need to be ready for this. So research projects for high school students here, it's actually quite uncommon. I know it is common in the United States and perhaps also in Canada. I don't know.
Yeah.
But it's less common here, and I think it's probably because we believe that people are not yet ready to do any
Right.
meaningful research at that stage. But I don't know. It's not in our system that we offer this at the moment. To high school students. Obviously, our own students do research projects, and already
Mhm.
after the first year. But we don't really have structures to offer this to high school students.
Right.
So I guess
Right.
I don't have enough experience to say whether it's useful or not. I think
Mhm.
if it's a project where the student is ready for it, and I think then it's great and it gives you. But if the student is not ready for it, it can also discourage people from it. So
Right.
my experience with offering, say, research projects for, say, first-year students, who, of course, at the end of first year, perhaps also not yet at a level they can go into a sort of very heavy, pure maths project and make progress on it. My experience is that computational projects, for example, they're easier at an earlier stage. So, if it's something
Mhm.
computational, something in numeric analysis, for example, you don't need such a big sort of grounding or foundation in order to, make meaningful progress in understanding these structures. So I guess it depends also on the type of project. So more computational, more on the applied side would probably work a lot better than trying to do something pure mathematics where you just need really the foundation of understanding these structures before you can do anything meaningful.
Right, totally. I mean, I think the best way to actually go through your mathematical endeavors is to, I would say, even having a good basic. I think high school is really a bit early, and I notice a lot of high school students doing that. I think they should probably um, build up their foundations, which is really, really important.
Yeah.
Yeah, but yeah, I think that is all for my questions. Thank you so much for answering them.